Welcome, everyone. We're going to be discussing the organization of the periodic table in this segment. First, we're going to start by talking about a Russian chemist named Dmitry Mendeleev. And what he is famous for is he was the first to publish a periodic table. What he did was he classified the elements and he arranged the elements according to increasing atomic mass. Now, the periodic table that Mendeleev developed does not look anything like today's modern periodic table. Today's modern periodic table, you'll see, is arranged by the concept of atomic number. At the time, that concept did not exist. Therefore, Mendeleev arranged them according to atomic mass. And some of the things that he did, which was at the time was pretty ingenious, was he would leave certain blanks in the periodic table. There were certain elements that were not discovered at the time, and he would predict those elements, and he would actually predict what properties that they would have. So those empty gaps, eventually, when they did get filled out, the properties that he predicted were actually very close to the actual elements after they were discovered. And that was one of the first things that Mendeleev did. The periodic table today, however, has been reorganized, and it's done according to atomic number instead of atomic mass. As you know, the atomic number has to do with the number of protons. Well, Henry Moseley, working in a lab, he had performed many experiments that allowed him to figure out the atomic number of several elements. And once he had these atomic numbers, he decided to go ahead and rearrange the periodic table according to atomic number instead of atomic mass. Now, what happens under Moseley's periodic table, which happens to be today's periodic table, is that the elements you will see are grouped into what we call families. And one of the things that I'm going to illustrate is that if you belong to a family, you share similar physical and chemical properties with all the members of that family. And this is proposed as the modern periodic law. The modern periodic law basically states that the chemical and physical properties of the elements are periodic functions of their atomic numbers. So today's periodic table, as you can see here, you'll notice the atomic number is the number right at the top over here, and the atomic mass is at the bottom. And you'll notice some discrepancies. I'm going to point two out over here. If you look at iodine and tellurium, you'll notice that according to Mendeleev, iodine would have come before tellurium because iodine has a lower atomic mass. But Moseley did not arrange it according to atomic mass. He arranged it according to atomic number. And despite the fact that iodine has a lower atomic mass, notice that iodine has an atomic number that's 53, which is higher than tellurium's 52. Iodine has 53 protons. So in Moseley's periodic table, you'll notice that hydrogen begins it with atomic number 1, and then recently we have this bottom group that have been synthesized in the lab, and oganesson, which is number 118, is the last one, but they are organized according to atomic number. Now, the other thing I'm going to point out is we want to look at the difference between what is called a period versus a group. And when you read the periodic table, a period is also known as a row, and it goes left to right. They are horizontal rows in the periodic table. You're going to notice that there are 7 periods, and they are numbered 1 through 7. If you look over here, you could see on the margin that the periods are numbered 1 through 7. And if you look at the first period, which goes across like this, you'll see there are only 2 elements. So period 1 only has hydrogen and helium. And then if you continue to look at the periodic table, periods 2 and period 3 have 8 elements each. Period 4 and 5 have 18 elements. So you could see that. You can just look at period 2. There's 1, 2, 3, 4, 5, 6, 7, 8. And so does period 3. 4 and 5, if you count the boxes, there are 18 in each. Now, here's where it gets a little tricky. Period 6 actually contains 32 elements, okay? And I'm going to show you something, because if you look here, there's this little arrow pointing at these 2 rows down here. And this first row is led by the element lanthanum. And this entire row is called the lanthanide series. But the lanthanide series actually is part of period 6. It actually belongs in this box right over here. So when you count all the boxes across period 6, and then you count the row or the elements that consist of the lanthanide series, you will see that you will count 32 boxes. So the lanthanide series is part of period 6, therefore there's 32 elements. Now on the bottom, you'll notice that in period 7, the element over here is called actinium, and this is known as the actinide series, and they belong in this box over here. They both belong in this group, which is actually group 3. We'll talk about groups in a moment, but the lanthanide and actinide series are in group 3. However, the lanthanide series is part of group 6, or I'm sorry, period 6, and the actinide series is part of period 7. So when we go back here, and we can scratch this off, because as of today, there are 32 elements also in period 7. The last few elements have been discovered in the last 20 years, and they're not natural. They are made in the lab. They're synthetic. They're very unstable. They're radioactive. And we now have filled completely period 7. The last element is number 118. You'll see it's oganesson is the name. OG is the symbol. So the lanthanide series belongs to period 6. And the actinide series belongs to period 7. So each of those periods hold a total of 32 elements. Now, a group or family is vertical. It goes up, down. They are vertical columns in the periodic table. Now, you saw that there were 7 periods going from left to right. However, there are 18 groups, and they are numbered on the top, 1 through 18. I mentioned earlier that if you belong to a group, you share similar and physical chemical properties with the members of that group, and I'll go ahead and illustrate that point in just a moment. So here we got another periodic table, and you'll notice it starts here. This will be group 1, and this all the way over here would be group 18. And these groups, which are also known as families, are given a name. Okay, we're going to go through that in just a second. But I do want to point out that the element hydrogen is placed here because it has something in common with the other members of group 1. Hydrogen can act as a metal by losing an electron. In fact, all the members of group 1 are known as the alkali metals, except for hydrogen, and I'm going to show you that right over here. So group 1 is the alkali metals, with the exception of hydrogen. And group 2 is known as the alkaline earth metals. Okay, so we'll go back over here and take a look at that. So you got the alkali metals in group 1, the alkaline earth metals in group 2. And one of the things that all the alkali metals have in common, even though hydrogen is not technically a metal, the reason it's placed there is because they all like to lose one electron. They all have a +1 charge. The alkaline earth metals, you will see, they like to have a +2 charge. Now, what that means is that alkali metals lose 1 electron versus the alkaline earth metals, they like to lose 2 electrons when they react. So there's a statement here that says the alkali metals are more reactive than the alkaline earth metals. Here's the reason. The alkali metals lose 1 versus 2 electrons. And if you think about it, it is so much easier to get rid of 1 electron than it is to get rid of 2. Since it's easier to get rid of 1 electron, that makes the alkali metals that much more reactive. All right, so let's take a look at groups 3 through 12. Group 3 through 12 are known as the transition elements or transition metals. So this is group 3 all the way to 12 over here. So that entire region is known as the transition metals or transition elements. Now, think about this. In group 3 over here, the lanthanide and actinide series belongs to group 3. So they are technically transition metals too. But in order to differentiate the regular transition metals that you see up here versus the lanthanide and actinide series, you will see that the lanthanide series and the actinide series are known as the inner transition metals. At the end of the day, they are part of group 3. They are transition elements, but the lanthanide series and actinide series are given a special name in that they are known as the inner transition metals. Okay? And then we go to the next few groups here. So this would be group 13 over here, followed by 14, 15, and 16. And it's funny because these 4 groups are named by the leader of the family. So if we look over here, let's go here to the names of these groups. Group 13 is led by boron, so it's known as the boron family. Group 14 is led by carbon, so it's known as the carbon family. Group 15 is led by nitrogen, so it's known as the nitrogen family. And group 16 is led by oxygen, which is known as the oxygen family. However, the oxygen family also has a more technical name, and it would be good for you to know this. The oxygen family is also known as the chalcogens. Okay, so that would be group 16. As far as what they do, when they react, they like to gain an electron. I'm sorry, 2 electrons. So they have a -2 charge. When you're negative, it means you're gaining electrons. So that would be the chalcogens or the oxygen family. Now that leaves us with, let me go back this way, with 2 more groups. And that is, they're side by side here. We got group 17 and then group 18. And with group 17, I know fluorine is the leader of the family, but it's not known as the fluorine family. In fact, they're known as the halogens. The halogens, what makes them react is they like to gain 1 electron, which makes them extremely reactive. Now, we'll talk about metals and nonmetals later, but the halogens are nonmetals. They are extremely reactive. And they're so reactive that you don't find them free in nature. In fact, instead of finding fluorine and chlorine and bromine on its own, they actually pair up with each other and they travel as a pair. So fluorine actually reacts with itself. And we see it in nature, we see it like that, not as an individual fluorine atom. The same thing we can say with chlorine. It pairs up with itself. And so does bromine and iodine. Now, there is also one other thing I want to mention about the halogens. And that is, as you go down, and I'll go right over here. As you go down the periodic table, okay, and I am right now drawing a little arrow pointing down, the reactivity of the halogens decreases. That means that fluorine is the most reactive halogen, and it makes, if you look down here, we'll talk about astatine, okay? AT down there is one of the least reactives, okay? So we're looking at reactivity decreasing as you go from top to bottom. Now, what does that mean for us? That means that the reactivity is decreasing, so the first 4 elements are diatomic because they are so they're so reactive that they pair up with each other. By the time you get to AT, it's not as reactive, and AT will already exist freely in nature. Now, fluorine at room temperature is a gas, and so is chlorine. Bromine is actually a liquid at room temperature, and iodine is a solid. So of this group, known as the halogens, fluorine is the most active of all of them. And what they all have in common is that they like to gain an electron. That's why they're -1 in charge. Now, here's the ironic thing. Group 17 is the most reactive group in the periodic table, but right next to them, their neighbors, which is group 18, they're known as the noble gases. And these guys are the complete opposite. They're known as inert gases. Inert simply means that they don't react. In fact, that's their chemical property. The fact that they do not react. They are not reactive at all. They're loners. And the leader is helium. And as you continue going down, you got helium, neon, argon, krypton, xenon, radon. We can now add oganesson to that list, even though that one's synthetic. But they are non-reactive. In fact, if you ever see a noble gas in a compound, it's a good chance that it was probably a man-made compound where the noble gas was forced to react. So here are the families. Remember, a period is 1 through 7. Periods go left to right. And then groups or families, it's 1 through 18, and they go up, down. Okay? And these families do have names, from alkali metals all the way to noble gases. Remember that hydrogen is the only one that technically doesn't really belong to a specific family. Now, one final thing about the periodic table. The periodic table is divided into metals, nonmetals, and metalloids. If you notice, the metals occupy basically the left side of the periodic table, with the exception of hydrogen. Even though hydrogen is there, hydrogen is a nonmetal. And most of the elements in the periodic table end up being metals. The nonmetals, as you can see, are on the right side of the periodic table. And then we got this zigzag line here that you see here in bold. And there's a few elements there. Okay, not too many. There's 8 elements there that border the zigzag line. You can see they're purple. One of the most popular ones is silicon, which is Si. And these guys are known as metalloids or semimetals. Now, to finish this discussion, let's go over just some brief properties about what it means to be a metal versus a nonmetal and a metalloid. Metals, we know, are on the left side of the periodic table, with the exception of hydrogen. And metals tend to be shiny. We call that luster. And when you are shiny or you have luster, that means that you have the ability to reflect light, and that's what makes them shiny. Metals are also good conductors of heat and electricity. Okay, in fact, one of the best conductors is copper. And if you look at your electrical wiring, copper is used so that it can conduct electricity when you have, cords, electrical cords in your house. Now, speaking of making a wire, if you look down here, this is another property about metals. They're ductile or ductility. That means that a metal can be drawn into fine wire. So you can make copper into a wire. There's other types of wires like aluminum wire, iron wire, chromium, and many others. But ductility or being ductile means that it can be drawn into a fine wire. Another thing, going back to number 3 here, is malleability. The word malleable means that you can hammer a metal into thin sheets. When you are hammering a metal, what you're doing is you're manipulating its shape. You can bend the metal, you can hammer it, and it will not break. It will not shatter. That's what malleable means. You can make them into thin sheets. Just think of aluminum foil, very thin sheet of aluminum. And basically, if you hammer it and if you manipulate it and bend it, it doesn't tear apart, or not tear apart, but break apart. And if you recall, most solids, okay, or most metals, okay, are solids. There's only one metal that at room temperature happens to be a liquid, and that's mercury, which is Hg. All the other metals at room temperature happen to be solids. Now, let's take a look at the nonmetals for a moment. The nonmetals are the opposite. They're on the right side of the periodic table, and they are not shiny. In fact, we can describe them as being dull. Okay, they have no metallic luster. And we talked about the ability of metals to conduct heat and electricity, but nonmetals, they cannot do either. They do not conduct heat nor electricity. In fact, if you get a nonmetal and you start to hammer it, it will crack, it will break. Okay? Therefore, not only can they not be malleable, they cannot be bent or hammered into thin sheets. You cannot make a wire out of a nonmetal because they are brittle. So brittle refers to when it's being hammered, it just shatters. So the shape cannot be manipulated. In fact, most nonmetals are gases. For instance, look at group 18, the noble gases, they're all gases. Now, there are a couple of solids that are nonmetals. I put carbon here. We saw earlier iodine happens to be another nonmetal that's solid at room temperature. We can throw sulfur in there too. There are a couple of nonmetals that are solids, but there's only one nonmetal that's a liquid, and that's bromine, which is Br. In fact, at room temperature, there's only 2 elements out of the 118 at room temperature that are liquids. One happens to be a metal, which is mercury, and the other one happens to be a nonmetal, which is bromine. Okay? And then finally, we have, you saw the purple. Okay, if you look over here, there are a few elements over here that border that zigzag line. And they're also known as either semi-metals or metalloids. And what they are, they're kind of like hybrids. They kind of have properties of both metals and non-metals. I'll give you an example. Silicon is a very good one here. Silicon, if you get a hammer and you hit it, it will shatter. It's brittle. It's not malleable. Okay, it's not ductile. So it has that property of being a non-metal. However, silicon can conduct heat and electricity. Now, not very well, but it can do it. In fact, it's known as a semiconductor. Now, the ability to conduct electricity does put it in the metallic category. So when you analyze silicon, you could see that it has a little bit of both. It can be metallic in that it can conduct electricity, but it can also be non-metallic because it's not malleable, it's brittle, and it will shatter, okay, upon being struck by a hammer. So as you can see, the majority of the elements are metals, okay, and one of the things you'll be learning in the future is that the metals, when they react, they like to lose electrons. So you'll learn that they like to become positively charged. The alkali metals like to be +1. The alkaline earth metals, which we talked about earlier, like to be +2. And then later you'll learn that the transition metals, they have multiple charges. Sometimes they lose 1, 2, 3, 4. Depends on the metalloid. I'm sorry, on the transition metal. And then over here you'll learn that the nonmetals, when they form ionic bonds, you'll see that they like to gain electrons. And when you gain electrons, you will become negative. Okay, you'll see that the halogens are actually the ones that are -1. The chalcogens, which we mentioned a little while ago, they actually like to gain 2 electrons. So when we go into bonding, chemical bonding, we'll talk about the preference of what metals like to do and nonmetals, what they like to do when they form an ionic bond. Okay, so hopefully this gives you a good, clear picture of how the periodic table is organized.